Right. Hello and welcome to lecture 9. Today's topic is very interesting, very important, especially in our community because most structures are built out of reinforced concrete. Today we're going to talk about how to design a structure using reinforced concrete. So by now, you guys have experienced design codes using different materials. What do you expect from like the design code to guide you? What do you expect the design process to be like? First, we will identify the structure member. Let's start with like beams, how to design a beam in Flexural. We will talk today about how to design it under bending, and then next week we will get into the rest of the checks. Do you expect what are the checks that you would do for a design of a structural beam made out of concrete? What are the steps?
Shear, bending.
Yes, bending, shear, deflection is not excessively deformed. All right, so can you build structures out of concrete? Yes, absolutely. It's one of the most durable construction materials. You can expect a life cycle of concrete to be significant. You can build high and tall buildings from reinforced concrete, and you can build the entire structure out of reinforced concrete. So you guys are familiar with how fresh concrete looks like, all the ingredients and how to mix it and everything. And then you can pour it into formworks to shape it the way you want. You can shape it into a slab, shape of a slab. You can shape it into a column, foundation, wall, and then you look at the structure and design each element in order for the load path, for the load transfer to find its way safely from whatever the load application is to the ground. So if the load is the weight of a person, so that weight of the person on the 3rd floor needs to safely find its way to the supports of the structure. That means the load needs to go through the slabs, and then through the columns. The columns will accumulate the load all the way to the foundation. You need to design the foundation that you size them. The size is reasonable for the stresses of the soil. If it's too small, it will sink in the soil. If it's too big, you're wasting material, and it's probably going to result in high stresses in the foundation. And you also look at the walls, which most probably you're going to use to resist lateral loads, like wind and earthquakes. So I need you to understand that design of reinforced concrete, this is a material. It's called reinforced concrete. It's different than just concrete. That's why there is such thing as minimum reinforcement. If you're designing reinforced concrete, you have to put at least minimum amount of reinforcement regardless of the load. Obviously, if the load is bigger, then you need to increase the reinforcement. So any guess why do we need minimum reinforcement? Why reinforced concrete behaves different than just pure concrete?
Carry tension.
What's that?
That steel bars carry tension inside the beam or the.
I like that very much. Yes, that's true. Reinforced concrete or concrete and steel, they will complement each other in a very important way. Tensile stresses are best suited to be resisted by steel. Steel is very strong in tension. Concrete is terrible in tension. Concrete almost have no strength in tension. As a matter of fact, if you put a load on an unreinforced concrete, it will just like crack into two, it will split into 2 halves in not a very big stress compared to steel. So whenever you have tensile stresses, you want to have reinforcement there. What concrete is good for is compression. It can take quite a bit of compression. So I want you to take a look and understand what is happening inside a section of a reinforced concrete. You expect to have a body of concrete with steel bars embedded, surrounded by concrete. So in reality, it would look something like this. The formwork, this is the void or the shape that will create the outline shape of the beam. And then inside, you have two main types of reinforcement. Horizontal reinforcement, top layer and bottom layer, the very top of the beam and the very bottom of the beam. And you have vertical or ties or links or stirrups. The Eurocode will call them links or stirrups. These are these double lines. Do you see like this kind of enclosed line? This represents the vertical lines, which we are going to be talking about next lecture when we design a beam for shear. The vertical links, the vertical stirrups will resist shear. The horizontal bars, the top layer or the very bottom layer, this will be resist the bending moment on the beam. Does that make sense? So if there is one thing I want you to understand from this shape or from this slide, is that when you take a cross section in a reinforced concrete beam, you expect to have few things. There is the overall dimension or the overall width of the section, and inside it there is a stirrup with longitudinal bars going into the page. So each black dot, this is a bar. This is a bar that is running along the beam. When you take a cross section, it will look like a black dot. And it will be your job to figure out how many bars do you need and what's the diameter of each bar. We will sum this up as the area of steel. What is the summation of all the bars, area of the reinforcement? We will learn today how to calculate the total area of steel to resist a certain bending moment on a cross section safely. Few more things I want to point out. There is a very critical distance, which is the distance from the bottom reinforcement to the bottom edge of the concrete. This is called the concrete cover. The concrete cover is very important for durability. It will dictate the fire resistance. In case of a fire, this cover will delay the heat transfer from the underside all the way to the steel, because if the heat gets to the steel, it will start expanding and yielding, and the member will lose its capacity. So in your design, you will have to decide what is the concrete cover. In a specific problem, I might tell you, okay, design a beam with this concrete cover, but I need you to know this is part of the design. How do you choose the concrete cover? What are the factors that you need to know to choose the correct concrete cover? Fire resistance, as I said, how many hours of resistance you need out of the structure, and durability as well. If this beam was buried in the ground, it's probably exposed to soil, different chemicals maybe, moisture. So you want to protect the steel. This is why there is a cover from the bottom side and cover from the both sides of the beam. This cover is very important to protect your steel. So if I ask you to draw the detail of a cross section of a beam and you put the bar right there at the edge, this is completely unacceptable for so many reasons. If you're building the structure and you put the rebar right there on the formworks and you don't leave a spacer for concrete to fill underneath the bars, you're causing big damage, big harm to the section. First of all, when you remove the formworks, your steel will be exposed. These bars, you will see them from the underside because they're so close to the underside. They will corrode much quicker. They're not protected from fire, from the environment. That's the first thing. The second thing is, in order for reinforced concrete to work, all bars in the concrete needs to be surrounded by concrete to develop bond. between the bar, the steel, and the surrounding concrete in order for it to work together. If your bar is too close to the edge, there is no enough concrete surrounding it to develop proper bond. What may happen is if you apply a load and the bar is too close to the edge, it might slip. Actually, delamination happens between the concrete and steel. To avoid that, you need to put sufficient cover. So I can't emphasize enough the importance of concrete cover. Very common mistake, especially at the beginning. You're attempting a design of a cross section. You don't know where to start. I would say like put at least an inch or 25 millimeters from the underside of the concrete to the stirrup, and then you add the thickness of the stirrup or the thickness of the link, which is the reinforcement for shear, and then you calculate the center line or the CG of reinforcement. This is the next step that we will need to calculate the depth of the section. So there are two values that you will need regarding the height of the section. There is the overall height from very top to the very bottom, but there is another value that you will need in the design, which is D. D is the distance from the very top of the concrete to the center line of reinforcement. Any guess how do we calculate D if we know the overall height of the cross section? Minus the cover. But remember, the cover is the underside of the bar. You just need to add it to the center line of the rebar. So I will consider the distance from the very bottom of the beam to the underside of the stirrup, then add the thickness of the stirrup, and then half the bar diameter to get the middle of the reinforcement area. This is how we find D. That's the first number that we will use. All right, so what's the theory here? How is concrete and steel going to work together? I think it's best represented when we talk about a rectangular section. And let's study under bending. So there is a bending moment applied on this section. And I want you to guess what is the stress distribution due to bending on a rectangular section. We've talked about this a few times. What do you expect is the stress distribution for a rectangular cross section? In the very elastic stage, how would that look like? E.
Two triangles.
Yes, that's pretty much it. If this is the shape of moment on the section, the top will have compression, the bottom will have tension. So at the very early stages under the elastic load, you will have compression stress at the top, compression stress at the bottom, and then the distribution is going to be linear. All right? Now, the tension, this is tension, this is compression. The tension stress, the amount of tension that concrete can take is very small. Very quickly, this will reach a stage that concrete cannot take tension anymore, and this will result in a crack. The crack will extend up to the point where there is no more tension. This line is called the neutral axe. The neutral axe. So what is the neutral axe? It's the neutral axe above which you'll have compression and below it there is tension. So very quickly, the concrete will pretty much lose any tension. It will lose all the tension. And the part that is resisting compression is just the part above the crack. because concrete is strong in compression, very weak in tension. So how do you hold that section together? You put a steel on the tension side. That's why it's very important when you draw the bending moment diagram, you understand where is the tension direction, because this is where the heavy reinforcement will be. So you will add a bar, this is a steel bar, to hold these cracks together, and the steel rebar will take the tension, and all the concrete will take the compression. Does that make any sense? So if you kind of look at how this section is going to work, the resultant of the compression here, or the compression stress, will have a compression force, and at the steel level, so this is, let me do it like that. This is the steel bar. At this level, that's going to be the tension force. This is the tension force in the steel bar, and above the neutral axe, there is the compression that is resisted by the concrete. In order for this section to be stable, in equilibrium, do you think there is a relationship between the amount of the compression force at the top and then the amount of the tension at the bottom? This is kind of tension. What's that? Why is that? That's an interesting thing to say. Why would you say the tension in the bar should equal the compression in the concrete?
So it's bending, so if you can't have it bending more from top and expanding less from the bottom.
Because you want this section to be in equilibrium. If one side is bigger than the other, then this beam is gonna keep on moving. In order for this section to be in equilibrium, the tension in the bar has to be equal to the compression at the top. There is one more thing that we can get out of this shape. What do you think is the maximum capacity or the moment that this section can resist? What is the couple that this section can resist under these two forces? Yes, on this section, let's say that this is the section that we are studying. What is the maximum moment that this section can resist? Do you guys want to include us in the discussion? No? Okay, what was the discussion about? Do you want to bring it to the conversation?
Just about the diagram, the stress diagram that presenting the compression at the top and the tension at the bottom.
Okay, I can go over it quickly. I just find it distracting when you have your own discussion on the side. So the diagram here is the stress distribution. What very quickly happened is concrete in tension will pretty much disappear. The reason it will disappear because there is a physical crack, there is a physical gap. So if you analyze a section at the crack, you'll find that the crack goes all the way to the bottom. And this is like a separation. This is like a separation in the concrete. So with section here, you'll have like part for compression, and then there is just the bar. Part for compression and just the bar. The answer to the question I was talking about is you can figure out the maximum moment that this section can resist by knowing that the compression force has to equal the tension force, and the maximum moment on the section has to be the tension or the compression multiplied by the distance between these two forces. So what is a moment? A moment is a force at a distance, or a couple, which is two equal forces at a distance. And this couple is either the tension or compression multiplied by this. The Eurocode calls this distance Z or Z.
زائد اللي هي من أول الكونكريت لحد الستيل بار؟
No, that's a good question. I need you to look closely and try to guess what Z is. Where is the distance Z measured from? From the compression force to the tension. Where is the tension? It's in the bar level. So I know that this force is the concrete cover distance from the bottom. This is the concrete cover from the bottom, and this will give us the location of the center of the area, the center of area of reinforcement. Perfect. So where is the location of the compression force? What is the distance between the compression force and the top of the section?
The distance of the cover, the center of the cover.
So the compression has nothing to do with any reinforcement, if any, at the top. The compression has to do with the depth of the crack. So the crack, if the crack is too tall, it will leave us with just a little bit of concrete, and the compression will have to do with whatever left. This is where you need a lot of research, a lot of testing of the behavior of concrete, and luckily, the design codes did a lot of work for us to define this distance. So the code will tell us how to design a section and what is the distance to the compression force. So before we go there, let's talk a little bit about how concrete will behave in compression and how tension or steel will behave in tension. You are probably familiar with the stress strain curves for both concrete and steel. The left side is for concrete, the right hand side for steel. These graphs represent the relationship between two things: the stress on a bar of steel and the strain, or like the elongation, how much it will increase in length. This is the typical stress strain curve for steel. It will go linear up to pretty much yield, and then it will have like significant elongation. Concrete is much less ductile. It will not move too much before it crushes into rubble, into dirt. This will happen if you apply a load on a cube or a cylinder of steel. It will continue to take the load, it will continue to take the load, and then suddenly it will show cracks and it will start crushing, and it will very quickly lose the stresses. Here is a very important design philosophy aspect that I need you to understand. You don't want concrete to fail first. There are two materials in your section: compression acting on concrete, tension acting on steel. You don't want your compression to crush concrete first. Because if concrete is crushed and steel, let's have more capacity, crushing or compression failure is very sudden. It will happen suddenly. It will not give occupants of the building ample warning that there are some cracks, like wait a minute, there's something happening. Concrete is more brittle. It will fail suddenly. So you don't want compression failure to govern the design. Therefore, you don't want concrete to reach that level first. You do want steel to reach yield first. The reason why, and that's something brilliant about steel. Steel, when it reaches yielding, it will show a lot of deformation before it actually fails. It will show very wide cracks before it gives up on the structure and the roof comes down. So you want that. You want to have a ductile failure. You want to limit the strain or the maximum stresses in concrete and allow steel to yield. Because once it yields, the more load you add onto it, it will keep its strength, but will just deform more. It will just deform more. So if you overload a floor designed properly to have failure in steel by yielding rather than compression failure, When it reached to the limit, you will find very wide cracks before the floor actually suddenly fails. So, what is the difference between the top and bottom diagrams? The top diagram is the actual behavior in the lab. The bottom diagram is the load idealized curve. So the code will tell us, okay, you don't need to kind of deal with steel that looks like that. Let's make it easier into a linear part and then a horizontal part. And let's take a factor of safety. Do you guys remember what is the gamma M for that we took for steel? What was the gamma factor for? Yes, when it was 1. What was that partial safety factor for?
Variation in steel, the variation in manufacturing.
It's a factor of safety for the material. It's the factor of safety for the strength of the material. In reinforced concrete structures, we will use the factor of safety for concrete as 1.5, meaning that we will divide whatever strength of concrete that you think you can achieve by 1.5. Why are we reducing it by that much? For steel, we were dividing by 1. For concrete, why are we dividing by 1.5?
Variation in manufacturing.
Because concrete is manufactured mostly kind of on site or in a concrete mix plant, which usually, most probably, will not have the tools or the possibility to have a quality control as much as the steel factory that will produce steel. So I need you to know 2 factors very important. The factor of safety for concrete material is 1.5, for steel is 1.15. So how do we use these factors? Rather than using the yield, the characteristic yield strength of steel, you divide it by gamma S. So if the characteristic steel, if F yield is 400 or 500 MPa, you don't use that number in the design. You reduce it. You reduce it by how much? Divided by 1.15. This is this number. Do you have a question?
Why are the steel and reinforced concrete are you dividing it by a factor of 1.15 when in the steel beams you only divide it by 1?
I love this question. Yes, that's a great question. Any thoughts? Why in steel structures we use the factor of safety as 1, but in reinforced concrete we're using 1.15? Aren't steel produced the same? Corrosion. So you're taking into account, so steel structures are not gonna corrode?
How exposure بيكون أكتر.
Exposure is more in reinforced concrete. I think the bars are embedded in concrete. Concrete is protecting steel quite a bit.
It makes more sense for it to be switched. Because steel and steel structures is exposed to the air and the external environment.
Okay.
When steel concrete isn't.
I've heard some interesting reasons. It could be part of the answer, but I would say who controls the amount of area of steel in a reinforced concrete beam? The designer will detail or put the information on the drawing, but the actual building, who is controlling the amount of steel in the beam? I would say the builders, the person that physically take the bar and put it there. So there is more human error. Someone could use the wrong dimension. Someone could miss a bar. Someone could miss the cover. The cover could be higher than it is or lower than it is. There is more variables that need a little bit higher factor of safety. So it's a good eye that you spotted the difference in the material factor of safety between steel structures and reinforced concrete. I would say the reason why the partial factor of safety for reinforced concrete is higher than steel structures is because there is more variation when it comes to reinforcing concrete with bars. Okay, so there is one more thing I need you to notice from this diagram. This is the code diagram. It tells us what is the maximum strain that the concrete can handle and the code will allow. What is the difference between stress and strain? If this is the stress distribution, this is stress. So what is the strain? What is the relationship between stress and strain? If this is the stress and this is the strain, what is the relationship between stress and strain? E, the modulus of elasticity. So the modulus of elasticity equals the stress over strain. So how do you calculate the strain? It's pretty much the stress divided by the modulus of elasticity. So the modulus of elasticity is like in the straight part, but past that part the behavior is different. The assumption that we will make is the strain and stress, the strain in concrete and steel is going to remain equal. If I can get your attention for a second, this is a very important concept. Because we assume there is bond between each bar, has appropriate bond between the concrete. So if one moves, the other will move as well. So we will consider that the strain is equal, equally distributed along the section, and therefore we're not going to have this sudden gap that we had in stress. We will assume that the strain in the concrete and steel are going to be equal. So the reason why I did this diagram is the code tells us in order to avoid compression failure, limit the concrete strain to 0.0035. This is the Euro code version. The Egyptian code will tell us to limit the strain only to 0.003. So what is that? That's the maximum strain that you allow in compression. If you exceed that part, you're at risk of having compression failure, which is something we are trying to avoid. All right, so where is that number come from? This number comes from the maximum strain. The bottom side is the strain, the top side is the stress. If this is the code idealized curve, the maximum strain is at this number over there. It's the strain CU2. It's the maximum strain that the concrete can handle, above which compression can happen. So where do we get this number? There is a table in this is the Eurocode version. It will tell us what is the strength of concrete or the class of concrete. So when I say the class of concrete is like 40/50, 40/50, what does that mean? Yes, that's right. Which is bigger? The cylinder is bigger, the cylinder strength is bigger, or the cube strength is bigger? Cube is bigger. So the smaller number is for the cylinder, and the second number is for the cube, and it represents the compressive stress, the maximum stress that concrete can take in compression. These are a whole bunch of properties of concrete, and the code gave us the formulas for it as well. But I want to highlight this maximum strain. It's 3.5, but you divide it by, it's not like percentage, it's like you divide it by 1,000. So the actual strain is 0.0035. This is what the code tells us to limit the maximum strain. This will be a very important aspect in the design of the section. So this is the diagram that I was trying to explain here. When you load a beam past the amount of tension that the concrete can take, it will crack. And the only thing keeping the bottom side is the steel reinforcement. That's why steel is very important. You want to protect it, you don't want to corrode, because if you lose it, then the whole thing will come down crumbling. This is more or less on a cracked section. What are the forces? How are the forces working? There is a compression force resisted by the concrete still intact, that compression force, and all the tension is resisted by the bar, by the steel bar. So you take a section here and you try to analyze it. Only the hatched part is intact concrete, capable of taking tension. All the unhatched part, this is part of the crack, like void. The two pieces are like separated. There's nothing in between, there's just the bar. Having said that, these cracks are very small to the point that you need to control the crack width, especially if your structure is going to be exposed to moisture or water. You don't want water to work its way through these cracks, cause damage to the reinforcement, which will very quickly reduce the capacity of the section. This is the idealized shape of forces on the section. Rather than looking at the stress, strain, the stress distribution in the linear part, and then as you exceed the stresses, the shape of the stress block, this is called the stress block, on the concrete will start to look like the compression curve for concrete. Do you remember that curve that we talked about? Do you see that shape? That's the relationship when you have very low stress, it's almost like linear, and then very high stress, it's curved. And this is exactly how the compression stresses look in the concrete. So rather than dealing with like a curve, the code makes our lives easier. It says, okay, you know what? Forget about this curve. Let's assume the stresses in the concrete compression to be like a block. And it will give us how much is the stress that we can use to be able to do two so important things. Figure out how much is the stress that concrete can take, and figure out the location of the compression force. Because once we figure out the compression force location, we can get the distance from compression to tension and figure out the moment capacity. So a lot of what I've said has been an introduction to get you to understand how reinforced concrete works, what to take into account when you're actually doing construction, where the bars goes, what's their purpose. But now I want to focus on the number crunching. How do we get to the ultimate moment capacity that you can use in your design? So in light of what you guys have experienced in previous design material or design codes, how do you design a member or a beam for bending, for flexion? What needs to happen? What are the things you need to design a beam under bending?
Moment.
What moment? You need two moments.
Due to compression and deflection.
You need the actual moment on the beam due to the load, and you need the moment capacity. You need the actual bending moment on the beam, and how much this beam can resist. Yes, the moment resistance. And that's what we're going to try to achieve. That's what I'm going to show you how you can calculate the moment capacity of a reinforced concrete section. What do you do with this capacity once you figure it out? You make sure that it's bigger than the actual moment on the beam. Does that make sense? So now we're going to focus on, with some reinforcement, with a dimension of a cross section, with a certain capacity of concrete, with compressive strength, and knowing the yield strength of steel, let's figure out how we can calculate the maximum bending capacity of the cross section. This is the equations for the Euro code. This is the equation for the Egyptian code. You will find a lot of similarities with very few differences. I can point you right away to the differences, The Egyptian code will limit the top strain to 0.003. The Eurocode will limit the top strain to 0.0035. Other than that, they are very similar. So what is happening here? First assumption is, let's not worry too much about curved shape of compression block. I'm interested to know how much the concrete is resisting in compression. And let's assume it's a block. It's like a rectangle multiplied by the width of the beam. Do you guys see why this block here or this block here needs to be multiplied by the width B? Because this stress is uniform across the beam. So when we try to calculate the compression force C, you will realize that we need to multiply by the width B to get the area of that block, to get the area of that cube. All right, so what do we do from here? We will need few basic information to figure out the moment. In order to get the moment, I need two things. I need the compression force, which should equal the tension force, and I also need the distance between the tension and compression, Z. Once I figure these three things, I can very quickly get the ultimate moment capacity. Let's see how we calculate the compression block. Can someone, let's focus on the Eurocode, because this is the example that we will do in the tutorial, and then you can very similarly apply it using these equations. How much is the force FC? 0.85. So what is that number? What is FCD? That's the width of the block. So how do I get the area of that cube? How do I get the area of that cube? Or like, not the area, the volume. How do I get the volume of that cube? What's the width of that cube? Yes, 0.85 FCK. What is FCK? Is the characteristic compressive strength of the concrete from this cylinder. What is that 1.5? Why do I divide it by 1.5?
The strength of concrete.
It's the factor of safety for concrete. Gamma C. This is gamma C, which we agreed to be 1.5. All right? Is there anything else in this term? This is the width. So is this the force, the compression force in that block? What's the other dimensions? What's the other dimensions of that block? Its depth is 0.8, the depth of the neutral axe. I already talked about the neutral axe. Do you guys remember what I said about the neutral axe? Above which is compression, below which is tension. There you go. So the depth of the block is 0.8, which is a code factor. The code pretty much says the depth of the block is 0.8, the distance x. The Egyptian code will call the same distance, we'll call it C, and A is the depth of the block. It's also 0.8, the same distance. So both codes, they agree in that assumption. All right? So if I want to calculate the volume of that block, now I have this dimension and I know the depth. So how do I get the volume? Knowing the depth and the width of the beam. How do you get a volume of a cube?
The area divided the width?
Yes, area times width. So what is the area of this side? It's 0.8 FCK divided by 1.5, that's the width, divided by the depth. How much is the depth?
0.8.
Yes, 0.8 x. What is x? It's the neutral axe. It's the depth of the neutral axe. This is x. All right. Is that the volume of the cube?
This is
Yes, there is one more dimension missing. Let's see if you can find it.
The length.
Yes, which is, what is the symbol for like the missing part?
S over 2.
S, Z,
B.
D.
D, is it D?
No, it's B.
It's B, all right? The width of that block is the width of the beam. What is the width of the beam? It's B, all right? And ladies and gentlemen, this is how you get the compression in the concrete. What is the tension in the steel? What is the tension force in the steel? It's very much the area of steel multiplied by the stresses in the steel. And since our design is based on the ductile failure or having yield develop in steel first, so we will assume that the tension in the rebar already reached yield. So it will be the area of steel multiplied by the yield stress divided by the factor of safety for steel. And this is the tension force in the concrete, in the steel rebar. So we already said that in order for the section to be in equilibrium, tension needs to be equal compression. So let's say I assume that area of steel is like 2 bars with a diameter of 20 millimeters or something. So I can start with some assumption here. I know the F yield for steel. I will order bars with a certain characteristic yield. So let's assume it's like 500 MPa. And we pretty much can, just by knowing the area of steel bars, we can know the tension at yield. So let's take a look at this equation. What if I order concrete with a certain capacity or with a certain characteristic compressive strength? Let's say concrete C40, 50 or something like that. So that means the cylinder compressive strength will be around 40 MPa. Let's say this beam is going to be part of a wall, and the wall, the architect wanted to be like 200 millimeter wide. So I can accommodate their design and say like, fine, I can build my beam to be, I can build the beam and the structure to be 200 millimeter wide, and therefore I can use this as an initial assumption. So when you look closely, the only thing that is missing is how much is the actual distance of the neutral axe. And that'll be like very important number to control. And what I mean by control, I mean you can have too big of an X that concrete will fail first. I already mentioned that you want to avoid compression failure. So how do you avoid compression failure? You avoid compression failure by making sure that the ratio between X and the depth, which is from the top fibers to the center line of the reinforcement, this should be less than or equal the maximum number. This maximum number we calculate from the strain distribution. I will limit the strain at the top, and then will allow the strain at the bottom to exceed yield strain, and therefore the distance X divided by the distance D, I should always limit this number. So in the example, you will find very quickly that we will use X to calculate this factor Z, and we will limit Z, the ratio between Z and D, to 0.95. What will happen if you exceed the maximum allowable ratio? So important, I need you to understand it, and I need you to answer this question. if anyone else asks you why it's a critical step in your design, when you're putting reinforcement, when you're choosing compressive strength, when you're increasing the depth, why is it so important to limit the ratio between the neutral axe to the depth? To avoid compression failure. To avoid compression failure. If you exceed this, the section will be called over-reinforced. That means you have too much steel for the depth. The steel will not yield, and it will, the section will fail in compression. So you always want to respect this. All right, so it will probably make much more sense when we do the numbers. We'll do that in the tutorial. I just want to give you a quick summary of how do you neatly kind of do step by step how to find these numbers. Do you have a question?
What's the max?
Yes, so let's control Z over D to be maximum. This is the maximum.
No, I mean in X over D.
In X over D, there is a relationship between Z and X. Z equals D minus 0.x. So the code will limit it to like something around 0.45, but it comes from this relationship. So once you know Z over D maximum, you can figure out what is X over D max. Does that make sense? So Z over D equals 1 minus 0.4x over D. So Z maximum, you can figure out what's the X over D max. So important step. So this step is also reflected in the very first step when you do the analysis. When you run these equations together, so this is the force of the compression force. I already got it here. This is the tensile force in the bar. I already got it here. They need to be equal. So I can develop an equation to calculate X, or the depth of the neutral axe. This equation, to simplify it, let's assume a factor called K. The factor K is the ratio between the actual moment on the cross section and the compressive strength, the characteristic compressive strength, divided by the width multiplied by d squared. And this factor K, it also needs to be limited. It's derived from the same ratio. The factor K should not exceed a certain limit. It should not exceed 0.167. What will happen if you exceed maximum K? What kind of failure?
Compression.
Compression failure. You want to avoid compression failure. Why do you want to avoid compression failure in reinforced concrete?
My cracks مرة.
Because compression failure is sudden, is a very brittle and violent, almost explosive failure. But yield failure will give a lot of deformation before the cable actually snaps. Okay, from there, we will use this equation to calculate the ratio between Z and D, which is the distance between the tension and compression force relative to the depth of the section, which is the distance from the very top to the area of steel. Once we do that, we can figure out the actual area of steel required from this equation, and I need you to do very important 2 checks before you leave the design problem. Check that the area steel you choose is bigger than a minimum area of reinforcement. And I talked about minimum reinforcement area before. Why is there a minimum required reinforcement regardless of what load is on the section? This is very important. And I need you to check that the area of steel you calculate is at least bigger than minimum. If it's less than minimum, use the minimum reinforcement. Why is there a minimum reinforcement? Because this material is called reinforced concrete. If there is no reinforcement, it's plain concrete and it behaves completely different. So you always need to have minimum reinforcement. This minimum reinforcement is to control cracking, to control shrinkage, to control the behavior, the other types of behavior of concrete. Like these cracks, if you don't put reinforcement, they will be very wide. So you need minimum reinforcement for that. There is another, which is the last check that you don't exceed a maximum reinforcement. So why there is such a thing as too much steel and so little steel. You need to be like in the perfect zone, less than maximum steel, more than minimum steel. I need you to do these two checks. Calculate the minimum steel, put above it, calculate maximum steel, make sure that you're less the maximum steel. Why there is a maximum area of steel? For two reasons. If you put too much steel, the steel bars will be too strong and you'll have compression failure. The second reason is if you put too much reinforcement in the bottom, you cannot fit the rebars together. This is like for constructability. You can have it as a percentage of the cross section. If you have a cross section of the beam and you put too much rebar, there will be no space for concrete to envelop properly each bar, which will take us to the last check is like make sure that the spacing between these two bars can fit the concrete to flow around it and create bond with each bar. All right? So that's pretty much it, what I wanted to say about this section. It will make more sense when we go through it. This is the summary of the equations, but you will need to go through an example to make sense of all of this. If you have any questions, please come see me. If not, I will see you in the tutorial. All right, see ya.